quantum recursion and quantum quantization.
Okay, so I changed the titles. Actually, this is a part of the original one. So I'm talking about quantum recursion and the second quantization. But I just focus on the basic ideas and some examples. First of all, happy birthday, Prakash. For this work, I'm very grateful to Prakash because last year Prakash visited me and he gave a short course on the second quantization, which is the major mathematical tools used in this work. But the course is only the 4 hours, but I spent 1 year to understand. Finally, I got something to say. So, thank you.
Also, you will be student in the course.
Not student. I mean the UN course.
Oh yes, student.
Yes. Like 2 students and 4 hours. Thank you. Thank you. So the recursion has been considered from the very beginning of the studies of quantum programming. For example, recursive procedure was introduced in Peter's quantum programming language, QPL. So now this is the very famous papers. And also Yuan and I did this termination analysis of quantum well loop in the finite dimensional Hilbert space. But the control flow of quantum recursion this quantum recursion is classical because the branching is determined by the outcomes of the quantum measurement. So this is this fits very well into the Peter's slogan, quantum delta and classical control. But the quantum control flow was first conceived by architecture and Prakash in their language, QPL. And they have 2 case constructs. One is a case. So this one measures qubit. So the control flow is determined by the outcome of the measurement. Then it's classical. But they also have this case cycle. So this construct analyzes the quantum delta without measure. So let's see some simple examples. The Harmonic gate can be implemented, written using this if cycle then else statement, and also gate and CNOT gate. The idea is we analyze this, for example, for this NOT gate, we analyze this qubit X along the orthogonal branches of it. But we have a different approach to define this the quantum control flow. So the idea is to introduce an external quantum coil. So the state space of this coil is the 2-dimensional Hilbert space, which is the span of ket0 and ket1. And then suppose we have the 2 unitary operator U0 and U1 acting on a quantum system. We call this system the principal system. So then we can define the quantum case statement using this quantum coil in this way. 0 to U0 acting on Q, 1 to U1 acting on Q. So it looks like very similar to the classical if then else. But the thing is here we can do the superposition of the ket0 and the ket1, and then in the sense we get the superposition of the U0Q and the U1Q. So the semantics of this, the quantum case statement is a unitary operator in this tensor product of HC and HQ. So HC is the state space of coin, and HQ is the state space of this principal systems. So this unitary acting on 0 per side, we get the ket0, U0 acting on per side. And if it apply to 1 per side, then we get ket per side and U1 acting on per side. we can also use this matrix representation. Then the U is just the diagonal matrix U0 and the U1. We can go the one step further to define this quantum choice. Now suppose we have a unitary operator U on this the quantum coordinate. So in this status space of a quantum coin, and then the quantum choice of U0Q and U1Q using this coimposing operator V is just the sequential composition of UC and the quantum case statement. So there are some interesting the connections between this quantum coin and the probabilistic choice, quantum choice and the probabilistic choice, but I'm not going into the details of that. What I want to emphasize is that the ideas of extended quantum coin is not a new idea. Actually, as early as in 1990s, this idea was used by physicists to define the superposition of time evolution, and also it has been widely used in the quantum work, the quantum algorithm community. But if here U0 and the U1 are unitary operators, if U1 and U1Q and U0Q and U1Q are replaced by the general quantum problems that may contain some quantum measurement, then the semantics of this quantum case statement is much more complicated. If you are interested in that, then you can look at the paper already put on the archive. Okay, so now we have the quantum case statement and also quantum choice. Then based on them, we can define a new kind of the notion of quantum recursion. Let's start from a simple example. So one-dimensional quantum work. As you know, one-dimensional random works can be described as the particle moving on a line marked by integers. At each step, it moves one position to left or right, depending on the the flip of coin. The simplest quantum work we call the Hadamard work is a quantum variant of one-dimensional random work. So the status space of this work is HD tensor HP. So HD again is the two-dimensional Hilbert space. It is spanned by the cat L and the cat R. So here L and R are used to indicate the direction left and the right. And then we have this HP. It is an infinite dimensional Hilbert space. So spanned by the cat N. So N is an integer used to indicate the position marked by the N. So the one step of the Hadamard work is just, that can be described by this, the operators W, which is the composition of T and the H tensor I. Here T is the translation. It is a unitary operator in this tensor product HD and HP. So T acting on the L N, then we get the L M minus 1, and if we apply to R M, then we get the R N plus 1. So you see, this operator is the unitary operator in this tensor product. Here H is the the Hadamard gate, so that's why we call it Hadamard work. So this one is the unitary operator in this directional space HD. Let's look at this the single step work operator in a different way. So we define the left and the right translation operator TL and TR. Now there are unitary operators in this position space HP. So this is different from the total translation operator. The total translation operator is the unitary operator on the the HD tends to HP, but the left and the right operator and the translation just in this position space. So TL acting on n, then we get n plus 1, n minus 1, and TRN is n plus 1. So then the translation operator, the total translation operator T can be seen as a quantum case statement. So we can write it in this way. And also the single step work operator W is just the quantum choice of this, the left translator and the right translator using the Hadamard operator as the cointusing operator. Then the Hadamard work can be described as the repeated application of operators W. So W is a single step of operator. Now we change the structure of the Hadamard work a little bit. So then we can define the unidirection recursive Hadamard work. So this work first run the cointusing operator, Hadamard operator HD. So this is the same as the Hadamard work. If the direction coin D is in the state L, then the work will move one step left. So this is again the same as in the Hadamard work. But if D is in the state cap R, then it moves one the position line, then followed by procedure preparing as the recursive work itself. So this the recursive Hadamard work can be seen as a recursive problem X described by this recursive equation. So X equals TLP. The quantum join of the TLP and the TRP followed by X itself using this cointusing operator HD. Now the question is how to solve this quantum recursive equation. So a standard, the method to solve this recursive equation is the syntactic approximation. If we have a recursive problem X described by this equation X equals Fx, then we can define the syntactic approximation. So the first one, the x0 is abort, and then xn plus 1 is in F we use xn to replace x, and then we get the syntactic approximation, and then the semantics of x is just the limit. Now we use this method to the recursive Hadamard work. So of course, the x0 is just the abort. The x1 we use the abort to replace the x in the declaration of equation. So we get this one, and then we put this one to the place of x. Then we get this one. Here you see that now we needed to introduce a new coin variable d1. So here we have coin d, but here we need a new coin d1. Otherwise, there will be the variable conflict. And then we can put this x2 in the place of x, and then we get x3. So again, we need to introduce a new coin variable d2. So we observe that we must continuously introduce the new coin to avoid the variable conflict. And the variables d1, d2, d3 must denote the identical particles. And the number of the coin particles that are needed in running this recursive work is unknown beforehand. Because we don't know when this the work will be terminated. So we need to consider the quantum system where the number of particles can may vary. Then what kind of the mathematical tools we need to use to deal with that? Fortunately, this mathematical tool was invented by a physicist 80 years ago. So that's the second conversation. Now in the quantum physics, there's a principle of symmetrization, which says that the state of n identical particles are either complete symmetry or complete antisymmetry, with respect to the permutation of the particles. If symmetric, then we call it bosons. If antisymmetric, then we call fermions. Okay, then suppose we have the H, which is the state space of the single particle, and for any permutation pi of 1 to n, we can define the the permutation operator p pi in this n particle state, state space. So H tensor n in a very natural way. Furthermore, we can define this symmetrization and antisymmetrization operators at S plus and S minus, which is just the summation of this permutation operators. But here we need to consider the symmetry or antisymmetry. If the symmetry, then we use this plus, and otherwise we use minus. So, as I said, we use the plus to denote the bosons and the minus to, for the fermions. Then we can write this symmetric, the state of n particles, psi 1, psi 2 to psi nv, which is just the image of psi 1 tensor psi 2 to psi n, and the symmetrization operator SV. And the state space of the n boson, or the fermions, is just the HV tensor I. So this is the image of H tensor n and the symmetrization SV. Now if we introduce the vacuum state, cat 0, and then the HV tensor 0 can be defined as this one-dimensional space, which is the span of the vacuum state. Now we can define the space of the states of a variable particle numbers, which is the Fock space, FVH equals to the direct sum of HV tensor n. We can also define this free Fock space. So here we don't have this symmetrization operators. So this is the space of fermion and the bosons and the fermion. Then what about the evolution of bosons and the fermion? So suppose we have this U, which is describe the evolution of a single particle. Then the evolution of n particle without a mutual interaction can be described by this the both-phase U. So it is defined in this way. So U acting to every the contaminant F psi 1 to psi n. It is very easy to verify that this operator U preserves the symmetry and antisymmetry. So it can be extended to the Fock space FV H or the freer Fock space Fh. So the operator U, as you can see, transform a state of m particle to the state of m particles, and the same the particle of the same lambdas. But we have this creation and annihilation operators, which can be used to describe the transition between the states of different particle numbers. So for each state psi in the H, which is the state space of a single particle, we have associated the creation operators as A star psi. It is defined in this way. So as you can see, this operator adds a particle to the system of n particles. So now here we see we have n plus 1 particle, and the annihilation operator A psi is just the conjugate of A star psi. So it is not so difficult to prove this. A psi acting on the vacuum is a vacuum. If it applies to psi 1 to psi n, then we get this one. So from here you see, so the annihilation operator decreases the number of particles by 1 unit. So it's an annihilation.
What's a small remark? Annihilation operator in vacuum gives you 0, not the vacuum.
Zero vacuum?
No, 0. 0, not the vacuum. Just need to remove the cat.
Right.
You are the bad teacher for a second time.
Right, I'm a teacher here. Okay, so now we have this second conversation that it can be used to define the semantics of quantum decay. Again, we come back to this example. So the recursive Hadamard work, then the semantics of this recursive Hadamard work is the operator in this. From the Fock space FV HD tensor HP to FD tensor HP. So you see here, in the classic case we only have one type of recursion, but in the quantum case, it's split into two types of the recursion. The first one is the bosonic recursion. The second one is fermionic recursion. So depends on what kind of particles you want to use to implement this direction points. That's interesting. Let's okay. So you see, this semantics is a mapping from from the Fock space tensor, the HP. HP is the position space. But here, it is the principal system. But maybe we only consider with the principal system, so we can define this principal system as semantics. For each state big psi in the Fock space F with HD, then we have this mapping X psi P. It maps the pure state to a partial density operator in the principal system. How to define this one? So we start from the big psi tensor, the small psi, and then we get this cat phi, and then we take this the density operator, and then trace out the Fock space. So we get the principal system semantics. So this mapping is called the principal system semantics of X with the coin initialization big psi. Okay, now we see again, we say example. So this example is, you know, the a little bit, I mean, the modification of the previous example. I mean, so we have this bidirectional recursive quantum work. So now this work is recursive for, the program X, which is specified. I mean, it is it is the, you know, the quantum choice of TLP and TRP followed by Y using this point posing operator HD. And Y is the, you know, the quantum choice of this TLP followed by X and TRP, again using this point posing operator HD. Now we see, you know, the how what's the principle? I mean, the system semantics if the point posing is initialized in the, you know, the coherent state of a boson. So here we only consider, you know, the bosonic recursion. For any state of psi in this H is the state space of a single particles, and then we have, you know, the corresponding coherent state of this is defined in this way. So here you see A star psi. So it is the creation operators apply, you know, the n times. Now suppose this work started from the position 0 and the coin are initialized in the coherent state of the boson corresponding to ket L. So L is the, you know, the left direction, and then we can compute this, you know, the principal system semantics, which is this partial density operator. I guess, I mean, not go further, but so very brief conclusion. Actually, some, you know, the problems for further studies. The first question, I mean, the first problem is what kind of problems can be solved, I mean, more conveniently by using this quantum recursion. One candidate is sorting. So quantum sorting has been, you know, the studied already by some, you know, the because, but in their models they don't have recursion at all. But you know, in the class case, sorting can be described by the, you know, the recursion pattern. So that's one problem. We can work on that. And the other one is can be built a kind of, you know, the whole logic for the quantum where loop defined using this quantum coin. So you know, Prakash already observed that the Fock space can serve as a model of a linear logic with exponential types. Is it possible to you know, to combine this work with the holological quantum problem without this you know, the coin? But I'm not sure. So the last one is what kind of you know, the physical system can be used to implement the quantum recursion. Here, you know, the coin must be continuously created. There are already some you know, the experiment implementing the quantum control for unknown subroutines using quantum coin, but of course they don't have this you know, the recursion. So that's the last question. Thank you.
Random walk. So I'm actually very intrigued by the difference between the bosonic and fermionic random walks. I mean, bosonic and fermionic coins. Did you actually calculate what happens if you use fermionic coins to the random walk?
Okay.
Does it make a physical observable difference?
You know, for this one, if we just have you know, the two you know, if we just have two direction, then there will be a problem. If we have only the finite the finite choice, then still have a problem because we have this Pauli the principle to exclude the same state of different
But these are new points. I see, but they're in the same.
Right, but they are identical particles.
That seems to be something one can get around.
Yeah.
By tagging them in some way. I don't know.
Right, but if we have the infinite many of if the state space of the coil is an infinite dimensional space, then we can consider this kind of the fermion. Otherwise, you always get
Other questions or comments? Yes, Gordon?
Did you have a general recursion construct or some kind in your language?
Oh yeah, we are doing this, and we want to prove something like the fixed point theorem, but not exactly
that's my question. Yeah.
not exactly the classical case. Let me just show you this. Sorry. This example.
Yeah.
Then, of course, we can have a kind of, the fixed point theorem, but not exactly the same as in the classic case, because if you consider this part, if you don't change the right hand side, and then you need to change a little bit the left hand side, because here we need to create a new the coin.
Yes.
So in a sense, you can add a creation operator on the left hand side. That's one choice. The other choice is you don't change this left hand side, but you can add the annihilation operators on the right hand side, and then we have kind of the fixed point theorem. Yes. Thank you.
Viv?
I was just going to say the physicists have calculated bosonic and fermionic quantum walks, but it's done a little differently than that. I think Yasser Omar and Siddhartha Bose is the paper you're looking for. Normally we use the coin, so I think you've created an example of recursion here, rather than necessarily doing exactly what the original quantum walk was designed as.
Right.
If you don't reuse the coin, you get the classical random walkout because there's no correlation between the successive steps if you put a new coin in each one. But it may be I've completely misunderstood your definition.
But for example, let me show you a little bit the most
false space guy.
Yeah. Well, yeah, you can do it also in quantized too.
So if we consider this, the quantum aware loops, then if we put the W here, which describe the interactions between the coin and the principal systems, then what happens?
Yes?
How about anionic quantum walks?
What?
Anionic quantum walks, where the base.
Oh, that's the Prakash asked it.
Oh, sorry.
So yeah.
Yanis Kakros has done work on that. You'll find some of the topological people with papers on anionic quantum walks as well.
Oh, you mean anion, not premium? So sorry.
Yeah.
I don't know. Never considered.
Is there someone over here? No, Peter?
Yes, I was just thinking that if you look at your scheme in the classical case, the set of allowable walks would form the Dyke monoids, which has a rather nice factual structure when you start drawing things on it. Dyke. D-Y-C-K.
Oh, D-Y-C-K.
I was wondering essentially what this would look like in this case, and what it would look like whether that would be the bosonic and fermionic cases.
But I don't know that dictate. So what? So maybe I can ask you later.
Okay.
So yeah.
Okay, are there any other questions or comments? So we have a break now, and then I will